Let's take a look at solids of a revolution. This is basically just the next level of taking the area between curves, except instead of doing area, we're going to now move into volumes. Now, before I move into the volume, let's do a quick review of our area between curves so we understand how this is operating, how this works. Area between curves basically says if you want to find the area, you can take your top function, which would be your f of x, minus your bottom function, which in this case is our g of x. You find that distance between them, and you can call that a height, and you multiply by a width. So in other words, this is an infinite sum of rectangles. And so let's take a look at this picture that I have drawn. If I can find the difference between f of x and g of x, I can establish a height. So I'm physically just finding that distance. And I'm going to continuously find distance after distance after distance all the way through here. And if you can imagine this, you're simply looking at a bunch of rectangles. In fact, an infinite number of rectangles that have these heights defined as f of x minus g of x. This is your height. Times the width. Well, each width is infinitesimally small. That's why we call it dx. This is your width. And so this structure, we're looking at nothing more than a width times a height, or length times width, however you want to say it, and you're summing them up from A to B. So you're starting here at A, and you're ending here at B, where these two things happen to intersect in this drawing. So you go from A to B, and you add all those up, and it was nothing more than adding up a bunch of rectangles, because height times width, rectangle after rectangle after rectangle. Now I do have the second part of this, where we're looking at area between curves, and this is going to be a right-left concept. So on the first one, we're doing top minus bottom. On this one, we're going to do right minus left. And when we do our boundaries, we would have to go bottom up. So on this picture, maybe I'm going to have it just start right here. We'll call this A, and we'll have this point of intersection be B. And so the same concept would happen here. As I am looking at this, I have the difference between this curve that I'm calling h of y and this curve that I'm calling m of y. That would give me a length. L-E-N-G-T-H, length. And then as I start to draw these rectangles, I'm just slicing this up, slicing it up, looking at all these rectangles that would be stacked here. I have a length. My height would just be a dy. So length, width, height, however you want to call it. And it's nothing more than a series of me adding those up. That's what the integral is saying. Add all those rectangles up that are calculated and defined as length, that's your h of y minus m of y, times a height, which is dy. And so I see all these rectangles being stacked. And the other thing that maybe I failed to mention, I know that they're dy's because it crashes into the y-axis. It's crashing into the y-axis. That's why that's an infinitesimally small value of dy. These were crashing into the x-axis, so they were infinitesimally small x values that I call dx's. Now the next level, we want to look at this and say, well, how can we apply this to finding volumes? If you want to define volumes, it's basically going to be the same concept. You can apply any geometric formula. If I have a graph here, maybe I have f of x looking like this, and g of x looking like this. So I've got my g of x, f of x. I can find those heights. And if you can imagine this, I have this. What happens if I decide that I want to come out of the paper? I can actually come out of the paper and create a two-dimensional object, like a piece of paper just coming up like this. And so I could call this a length. The H would be a height. And my dx would be a width. That's 3 dimensions. Length, height, width. So if I have this come out and I define this, maybe I say I want it to come out 5 units. Every time it comes out 5 units. Just like that. And then you could do another one here. And it comes out another 5 units. It always comes out 5 units in this example that I'm doing. I know it's a little hard to see, but if you start to visualize that, if you can see what's going on, if I have a bunch of these little rectangles that are being summed up, and I'm using 3 dimensions on this, you can almost see how that would come out. I don't know if you could do that with like a 3-dimensional printer, those 3D printers, but this would actually sit right on the paper and come out like this. You connect all those up, and it goes back down. These would all connect up and go back down, creating this 3-dimensional object, which would be a volume because it has the 3 dimensions. I do the length, I do a height, I do a width. Now I've got another one of these here. I look at this formula. I'm just going to draw another picture. I'm just trying to formulate the understanding. I'm not so much worried about the math in this first video. It's all about the concept. So let's start with this. We'll call it f of x here. Maybe we'll have this parabolic shape going on. And then let's do a line, linear function just shooting through there like this. So this will be our A. This could be our B. And if you're looking up here, here's my drawing. If you're looking up here, it says half f of x minus g of x times h dx. Well, this f of x minus d of x, that's just going to be a length here that is taking the difference between the parabola and the line. So I'm doing these lines here again. You notice that I spread these a little bit further out so you can see what's going on. What would half a length, or maybe we should call it a base. Let's call it a base. Half a base times a height. What is that referring to? Half base times height. Those would be like triangles. So maybe I have these triangles that are shooting out 3-dimensional. So these are actually shooting out from the paper. They're coming up this way. And as you look at this, you could create this 3-dimensional object that shoots out of the paper. Literally just sits right on my paper. The base is on that paper and it shoots out this way. That would be 3 dimensions. The half doesn't count as the dimension, but I've got this base, I've got this height, and the dx means that you have triangle after triangle after triangle that's being stacked right beside itself, going all the way across until you fill this entire region. And so this would be a width. The dx is a width. 1, 2, 3 dimensions, which creates a volume. That's a volume. Now we're going to come back and actually revisit this concept, but we're going to do it after you get very familiar with something called solids of revolution. Now, solids of revolution, we did all that so we could start this concept here. And the concept is that with a solid of revolution, solids of revolution, you can have a formula that says your volume is equal to the integral from x equals a to x equals b pi r squared h. Now I'm generically writing this, and then I'm quickly going to change this into a calculus concept. We'll say volume is equal to the integral from x equal a to x equal b of pi. Remember, pi is just a number, so pi could actually be pulled out in front of our integral. The r, well, that's going to be your function. You're going to have to decide your function, and usually when you do solids of revolution, the way we'll start revolving about the x-axis, and then we'll do y-axis, and then we can do other lines. But we'll start with this. We'll say f of x, it's going to be your axis of revolution. Your axis of revolution. And what I mean by that is you have to figure out what your radius is based off of your axis of revolution. So in these first couple examples, I'm just going to say f of x that gets squared, and your h, because you're going to stack these, would be dx. So that would be your calculus formula. Now let's look at an example of this. So I want to find the volume. Maybe I have this radical that just looks like this. Real simple, y equals radical x. And I want to go from x equals 0. So I want to start here at x equals 0. And I want to stop at x equals 4. So I've got this region right here that I want to revolve about the x-axis. Again, a lot of this just takes some mental fortitude. You've got to visualize what you're actually doing. If I take this area and it starts getting swept around the x-axis, so you imagine this as a solid region right here. This is an area. It's an area, and I'm revolving it. You put this like on a drill bit, and you have this region right here that starts spinning around very quickly. As that spins around, it's going to sweep out a volume that almost looks like a bullet shape. Because this is going to go around like that. It's going to sweep out this bullet shape. And if you're looking at this as stacking, like we've done in the previous part of this conversation, you're really just creating a bunch of discs. It's one disc on top of another. And think about that. Let me turn the paper like this for a second. What if I had a disc, a cylinder right there, and then I had another cylinder? I'm talking about being over here. I'm just trying to draw it here so you can see it. And another one, and another one. Almost like you stack one of those wedding cakes or birthday cakes that you see on television all the time. You're stacking layer after layer of these cylinders, of these discs. This is oftentimes called the disc method, because what you are doing, you are simply finding that radius from your axis of revolution. This would be my radius at any given point. We call that x at that point right there. I run up to that function, and I'm looking at this as pi r squared, which we know that's a circle, times the h, where the h is your dx, that's your width. That's creating these discs that are infinitesimally small. And by stacking them, you would be able to find the volume of this region. You simply say the volume is equal to the integral from 0 to 4. My radius is going to be the function radical x that gets squared dx. Let me see what happened to the pi. The pi I can put right in the front, because remember, a pi is a number. You can always pull a scalar out. Now before I do my integration, let me go ahead and square this. If you square the square root of x, you just get x. So you're looking at volume equaling pi, the integral from 0 to 4, x dx. Now if we talk about, I'm going to squeeze this in here rather than waste another piece of paper. If we talk about integrating this, I can simply say this is pi. If if I integrate x, it's 1/2 x squared from 0 to 4. I'm going to leave the pi out for a second. If I throw a 4 in there, 4 squared is 16, half of 16 is 8, minus, throw a 0 in there, 0 squared is 0, half of 0 is still 0, which tells me that this volume would be 8 pi units cubed. I can actually figure out that volume there. Now that's our introduction to solids of revolution.